Right, guys. All comfortable so far? Okay. So I think what is going on with your labs is that your labs this year is one week early. So that is why we are repeatedly coming against constraints from the lab. But that is fine. I think the way we are organizing this, there's a logical consistency to that. So we'll just follow on with this. I think this will happen again in next week's lab as well. So that is my calculation. And next week's lab probably I am taking. So I have more control over what I do. But we'll just go with the flow. So essentially what is happening is that lecture notes 10 and 11 we are going to do later on, right? So to look at the positives of that, I think lecture notes 10 and 11 are somewhat lighter in terms of, certainly in terms of number of slides, but also in terms of concepts because you are already going through quite a few of those concepts. So I suspect that on lecture day 5, we will have quite a bit of time left to go through the entire material again, to address exam type questions and so on and so forth. So let's take the positives from that and move forward for the moment, right? Okay, so I think this is what we need to do, right? Okay, so what we're going to do today is we'll do a little bit of nonlinear GMM. It should be relatively light for you guys now, right? So I'll come to it in a few minutes and then you will see. We'll do a little bit of general discussion of concepts and then go into nonlinear GMM. Because you guys have already done GMM and just done GMM, this should be relatively light. Okay? We have also in passing discussed concepts of identification and so on and so forth. We'll be coming back to a more elaborate discussion of that a bit later. But that is how we'll proceed. Once we have done nonlinear GMM, we'll move straight to maximum likelihood. And your lab material tomorrow will include material from maximum likelihood. So that is why we need to do it this way. All right, okay. So far so good? Okay, good. We are not even started, right? Okay, so there is a typo on this slide. Maximum likelihood will really be lecture 13, not 14. Okay, so that's a small typo. We are going to do a little bit of the typology. This typology is important, right? We're talking about extremum estimators, classical minimum distance estimators, GMM estimators, M estimators, maximum likelihood estimators, etc. We're coming back to this again when we do maximum likelihood. And then we'll be covering a GMM, the general nonlinear case. See, we'll see how it goes, but I will be doing, I think, the example only in passing, right? Because the concepts you guys already have, right? The important thing is that what we'll find here is that the moment conditions are nonlinear, right? Okay, so and then, so what happens if moment conditions are nonlinear? Anything, any ideas? See, the point of the moment conditions is that the moment conditions are just equations which relate the error to the data, right? Okay, and expected value equal to 0. When we have linear moment conditions, what happens? we can directly relate that to sample moments. Guys, are you together? All right. If it is linear, we can directly relate it to sample moments. If it is nonlinear, what changes? Well, what changes is that we have to take first derivatives and equate these, the first derivatives to 0, essentially, right? Okay, so that is what we are going to do. But that apart, it is all very simple. There is a little bit of additional notation which comes in because these moment conditions are nonlinear, but otherwise the concepts are very similar. Okay. The slightly more critical bit here is that in a linear world, it is easy to calculate how many constraints are there, right? In a nonlinear world, it is going to be slightly more tricky. Okay, so the degrees of freedom, adjustments, and so on and so forth will be slightly more tricky. We'll talk about degrees of, so the degrees of freedom adjustments will be with respect to the first derivatives, right? So it will not be with respect to the underlying nonlinear equations. Okay, so we'll come to that. Okay. Nonlinear GMM, Hayashi chapter 7. And in his online text, in Hansen's online textbook, there is also an exposition, concise exposition. Other things are standard. All right. Key concepts. Some of these concepts we are going to take on when we go to maximum likelihood. So nonlinear GMM, nonlinear zero mean moment conditions. And then we're going to talk about information sets, generalized nonlinear IV estimator. And then really, the rest of this runs naturally onto maximum likelihood, right? So I should not have kept this stuff here. So it is only up to number 4. Okay, so I'm going to make some changes to these slides later on, okay? Right. GMM terminology, there are terminology issues, so our Hayashi chapters 1 to 6, loosely we are following that. Our parameter vector is beta. The true beta appears in the data generating process, in the model that we have written down. Beta hat is an estimator, any estimator. And our specific choice of estimator is beta hat naught. All right. We know what beta hat naught is when we do standard GMM. And we are going to take that little bit additional step to nonlinear world here. Okay. So this is our notation. And see, if you look at a traditional ML extremum estimator terminology, this is exactly aligned to this, but notation is slightly different. Again, we are emphasizing the differences in notations just so that you guys are not confused when you read different books. Okay, so this is our terminology here. Okay, so what is an extremum estimator? An extremum estimator is just anything which maximizes an objective function. Now this is an estimator of this theta guy, right? So it should, the objective function should include theta, right? But in the objective function, theta is an unknown. What is the data? The data are W. And it is indexed by n. Because it is going to depend on sample size, right? The properties of the estimator is going to depend on sample size. Okay, so it's indexed by n. So Wi is data, Yi, Xi, Zi, for example, and W is the full data set of n observations. Okay. Not to confuse this guy here, the data W with the weight W, capital W, right? Don't get confused there, right? Okay, so that is the only thing to mention, right? Okay, so this is our general definition of an extremum estimator. what kind of estimators are we talking about here? Well, classical minimum distance estimators, for example. I have two here. Well, I have GMM here, but you can also imagine straight away that OLS is also in this category, right? Okay, it is just, minimizing an objective function. Minimizing an objective function is maximizing minus of that objective function, so it is the same thing, right? It is maximizing some objective function, all right? So these are called classical minimum distance estimators. And there are M estimators, which are sort of similar, but they maximize a different kind of quantity, and we are going to come back to these in a little bit, right? Nonlinear least squares we are going to do here, there will be just one slide, it is just for information, and then we are going to spend more time on maximum likelihood. Right. So classical minimum distance, what is minimum distance? Minimum distance is a scalar, right? So how do you get a scalar objective function? Well, what you do is you take some distances. So these guys are distances, right? Remember in the GMM case, these were distances of the empirical moment conditions from the theoretical moment conditions, right? So there are those distances. And typically there can be many such distances. So how do we combine them? We take sum of squares. But not quite. We take sum of weighted squares. And this is a weights matrix that corresponds to that. Okay? And some of these guys may be related to each other. So typically the weights matrix can have off-diagonal elements as well, right? So to account for the dependence between the different objectives. So you are basically maximizing multiple objectives, right? So you write this as a distance, you want to minimize this distance, scaled suitably, right? But it is a argmax, so in order to be consistent with the notation, we put a minus here, that's all. Okay, so nothing funny going on. Right. Obviously, GMM is a special case of this. Right? So this guy here, in that case, will be this G bar n, which is kind of a sample mean. Okay? But that's about it. So you guys understand this, right? So this is very simple, right? And if you were asked to, if you wanted to put OLS, for example, least squares in the same framework, that is very easy, right? So you can do that straight away. Okay, so that is straightforward. Okay? Together? So that is a classical minimum distance estimator. Now let us talk about another class of estimators, which are called M estimators. M here stands for a moment, or think of it as a mean. So what do you do here? You take a sample moment that you can only calculate if you know the true theta. So sample moment, which is a function, of course, of the sample data, but also a function of the underlying true parameter. And then what we do is that we take the average, so that makes it a sample moment, and we want to minimize this. Okay? Please note the distinction of this class of estimators from the classical minimum distance estimators, right? So the mechanism that we follow to show properties of these kinds of estimators will be different from classical minimum distance, right? So for classical minimum distance, there's a certain mechanism. Guys have already seen that mechanism, right, to do as consistency, asymptotic normality. Here it is going to be slightly different. Here, in some ways, it is going to be, well, I wouldn't say easier. This is just different, right? It is easier insofar as we are very used to handling sampling moments, sample moments, right? So, you know, it's asymptotic properties and so on and so forth. Okay. Maximum likelihood falls in this category. In that case, we are going to see soon that this guy, this m guy is log of some density function or a likelihood function. Nonlinear least squares as well, right? Where this guy is minus epsilon I square, right? So things like this. Okay, so we are going to consider GMM and ML in detail. Okay, back to GMM then. This is the general nonlinear case. Now I'll point out only the major differences from the linear case. Right? The estimator is similar, so there is a objective function here, minimum distance objective function. This minimum distance objective function is like this. So far, our moment conditions were linear. So we had expected value of gi equal to 0. Corresponding to that, we had written this gn bar beta, which is this, and our gi was the zi epsilon I. Right? Now we are in the nonlinear world. Okay? So, what we are going to do is, we are going to say that we are going to set any arbitrary function of gi function of beta is equal to 0. These functions can be nonlinear. Okay? And corresponding to this, we can write down this gn bar as well. Okay? Right. In linear GMM, our gi was like this, zi epsilon I. Nice and simple. In nonlinear GMM, it is going to be a bit more complicated. This gi beta will be a function of yi, xi, zi, and beta, a nonlinear function. And our gn bar will simply be the average of this guy, sample average, which will be like this. This will, in the nonlinear world, be a bit complicated, right, because it's nonlinear. So we are not going to get closed form solutions like we had earlier, right? So we'll use numerical maximization here, okay? So how do we do that? Well, by taking derivatives, right? The nonlinear function, we convert that into a linear function. Okay, so that is what we are going to do. So what does that entail? So this G is a vector of derivatives, partial derivatives of this set of moment conditions, nonlinear now, with respect to beta, evaluated at the true beta. Okay? So now this G guy is a vector, right? How large is the vector? Well, it is as many elements as there are elements in beta, right? Okay? So it's 1 for every element of the beta vector. And correspondingly, there's going to be this Gn beta naught, which is evaluated, the same thing evaluated at some beta naught. Okay? If you have a particular estimator, then G hat will be just simply you substitute this beta hat for your beta, right? Okay. So where is the complication? Well, the complication is just in the fact that when we had the linear case, this beta basically dropped out. Why did it drop out? Because every element corresponded to, so the moment conditions were linear, right? So, kind of there was no beta staying on here, right? Okay, so there was an, this kinds of moment conditions were there, and the beta basically dropped out of that, right? So that was the simplification that we had earlier, which we are no longer going to have here. So we need an S, right? And what are we going to do? Well, S is simply going to be our modified moment, not moment conditions, moment equations, right? So those things, they are asymptotic covariance metrics. And let us say we somehow have a consistent estimator of this guy, right, which we call S hat. What is that? That is an estimate of this asymptotic variance of these moment conditions, nonlinear moment conditions, right? And other than these, the methods that we have looked at so far just carry through, right? Simple. The S hat is going to be just like this. Okay, so you have to take a derivative, right? That's it. So beta hat is some first step inefficient but consistent estimator. Okay, so for example, like before, using an identity matrix, right, for your W. Right. So this is S hat here. This was our S hat earlier. See, there was a simplification earlier, right? But this is not a disaster really, means this is just first order derivatives. Okay, so it's simple. Okay, so the inefficient nonlinear GMM estimator is consistent, asymptotically normal with a sandwich type estimator, right? And the asymptotic variance of that is this guy. Now everything is expressed in terms of this G guy comes in, right? So G is a vector of first order derivatives. And that is simply estimated by substituting the estimators for this G's. Okay. Efficiency, as usual, will be obtained by plugging in an optimal S or S inverse. All right, and how you do that is exactly similar to the linear case. Okay, so nothing more intricate going on here. Okay. So what is the generalized nonlinear IV estimator then? So this was our linear GMM, right? A nonlinear case has some complicated functions, right? So they are not going to be like this. They are nonlinear functions, and therefore we have to take their derivatives. Okay. So generalized nonlinear IV estimator then is simply as a special case of nonlinear GMM, right, where you use instruments for your respective terms in the this guy basically. Okay, but the disturbance there can come from a nonlinear model. There is elaborate discussion of one application here. I am thinking I'll go through this very briefly now. What I'm going to do is later on, I'm going to append some more slides here to indicate a longer discussion of this. All right, so that I will do probably next week, right? So you'll find that there will be a longer discussion of this application. Okay. Okay. And this is the typical kind of estimation that you find in many economic models. Here it is a consumption-Euler equation. What are individual consumers maximizing? They are maximizing the value of consumption going all periods up to infinity, suitably discounted, right? So you bring it down to current value terms, okay? And there is a discount rate here. And there will be a budget constraint under which this is optimized. Okay, so that is. What do we have here? The important things are rate of return on an asset. So you are investing an asset, and you have labor income, right? So you are taking your consumption, foregone consumption, and investing that into an asset with a certain degree of return, rate of return. And this omega t here corresponds to, so how are you doing this optimization? You are doing this subject to the information set at time t, right? You don't know the future, right? So that is kind of the rational expectations world, okay? The important thing is that the expectations are conditional on the information set which is available at the current time, right? So nothing from the future comes in here. So this is a rational expectations model, right? Strictly rational expectations model. Okay, you take first order derivatives of this for maximization and you get the Euler equation which is of this form, okay? Now we have to specialize to certain kinds of utility functions, right? And the example here, it uses a constant relative risk aversion utility function, which is of this form. Not because we particularly believe in that utility function, but because it makes life simpler, right? So this is a lecture, okay? Right, if you do that, then these things simplify, and this is what you get. There are important benchmark cases. Gamma equal to 1 is an useful benchmark because this thing happens, and then you therefore get log utility in that case, right? So that is one interesting benchmark. So effectively, this is our rational expectations model. Okay, so let us slightly rewrite this by setting this epsilon t as this guy here. Okay, so this guy here, we are writing this as an epsilon t. Okay, so what are we doing? What are individual maximizers doing? They are setting this expected value to 0, right? What are the parameters here? There are two parameters, beta and gamma. And you can straight away see that why nonlinear GMM needs to be applied here, because this is a highly nonlinear function, right? Okay. Okay. So why GMM? Well, GMM because the essential nature of the problem is a GMM problem, right? Because the how the problem is set up here is in terms of a conditional expectation. So because we have that conditional expectation directly, right, we take those moment conditions, corresponding moment conditions, and then proceed. Okay. Okay. So let us pick some variable zt from the information set, and this thing is exogenous, right? It is when maximization is happening, utility maximization at time t, this is already part of the information set, so it is exogenous to the decision making process. It can be literally anything, right, from the past. Okay, so then we can get this unconditional moment condition like this, right? So expected value of zt epsilon t, then we do this iterated expectations business here, right? And then get that this is 0, where this epsilon t is like this. Now we can do this for any variable in this information set omega t. So there are many moment conditions here. So these are our unconditional orthogonality conditions. Okay. Zt is a vector of L chosen orthogonality conditions. Okay. Greater than or equal to 2y, because there are 2 parameters we are estimating, right? So without at least 2 moment conditions, we will not get identification here, right? So we need at least 2. And then we can estimate this by generalized nonlinear IV in the form that we have discussed earlier, right? So it's a straightforward application. So in this case, see, because we have written down the moment condition in this form, GMM is available, but also nonlinear IV is available, right? Because the IV or the exogenous variables are linearly related to the errors, right? So directly in this way, all right? Also note that the orthogonality conditions, where do the orthogonality conditions come from? They come from theory here, right? Okay, so we have taken a representative agent problem, written down the rational expectations solution for that, all right? And the rational expectation solution directly gives us some moment conditions, which we are imposing here. So we are not imposing anything from outside. Okay, so this is directly corresponding to theory. All right? Note also that we have not assumed anything else other than these moment conditions coming from theory. Okay, let me stop here just for half a minute perhaps for us to recognize the importance of these two notes. So when we did ordinary least squares, what did we do? Well, we just took some data. We looked at some model that we had in mind. We do not know where that model came from. It came from past experience. It came from our dreams. It came from somewhere. A linear model, but the same thing happens for nonlinear models as well, and we are going to go into nonlinear models in a little bit. Then you are going to see. Here, however, where did our objective function come from? That came from theory. When we were doing OLS, what else did we do? Well, we cheated a little bit. We didn't say, but in some ways we assumed that our regressors were orthogonal to the error term. Right? When you write down the ordinary least squares objective function, that is not transparent at all. But we had actually assumed some moment conditions there. Okay? And having done that, then we did our OLS. OLS was fine. Then in order to do inferences, what did we do? We invented another condition, again from our imagination, that our errors were homoscedastic. Because our errors were homoscedastic, we could now get an estimator of the variance of the error. Okay? And having obtained the variance of the error, now we could do our t-test to find out which beta coefficients were statistically significant. Okay. As opposed to that, what are we doing in GMM? Well, first of all, the theory generates the equation that we want to estimate. Theory also generates the moment conditions. We have not assumed anything else about the errors. We have not assumed homoscedasticity as well, right? However, depending on what we assume for the errors, for the variance of errors, we have different estimates, right? For efficiency, we had to rely on some estimates. But most importantly, perhaps, we did not make any distributional assumptions at all. Our errors were not normal, not necessarily normal. They satisfy certain moment conditions. We were relatively agnostic about those moment conditions. At the same time, we were very clear about writing them down. Right? So we know what moment conditions we have assumed. We have certainly not assumed any distributions. An interesting question then is, suppose we were able to assume distributions, would that give us any benefit? So I'm not going to delve on that problem just now, but we are going to come back to this problem later today. Alright, so we are going to try and quantify what benefits we could have obtained if we had assumed something about the error terms, but for the moment we do not. Okay, what else? What variable should you use for ZT? That is a difficult question, right? Because, consumers, where do they get information from? It's anything in the past, right? Okay, so literally there's a lot which is available. However, anything in the past will of course work because they are in the past and therefore exogenous. Unless they affect behavior, unless expectations of what happens in the future affects these past things. How do we figure that out? Well, of course, we know that the Sargan-Hansen test is going to give us an idea about that, so we are going to do the J-test. However, still, another problem stays, which is that the finite sample performance can be pretty poor if we do not include proper instruments. So we can have a weak instruments problem, or weak identification may result. So we have to be careful as to what we choose as instruments here. What are the L variables? Typically you would have an intercept. Okay, you would have these kinds of things. What are these? These are growth rates of consumption. Why are they important? Because consumption, there's habit persistence in consumption, right? Strong habit persistence. Okay. Returns, there are lags. How many lags? I don't know, right? Presumably it is going to be different for different agents. So in our aggregate model, what we should include is something that we have to ask. Who do we ask? Typically, we ask the data. How do we ask the data? Well, by cleverly using the J-test and cleverly using weak identification inference, which I have not talked about. But I'm going to come back to that later on. That will be lecture 10. All right? Okay. Suppose we suspect serial correlation, then that is going to inform our choice of S hat. In this case, we are going to use potentially a hack estimator. I am not going to talk more about this as well, because then that takes us into econometrics too. You guys are going to do that later on. Okay? Okay. So if the equation is over-identified, and typically we would like to make it over-identified, we get a Hansen-Surgen J statistic and we can test model specification. Okay? So far so good? Right? That is all about nonlinear GMM, right? Very simple extension of the linear GMM case. Okay? Just one slide now, just for completeness, and reference nonlinear least squares. Okay, so WI is data observation, partitioned into YI, XI. YI is observations and XI is regressors. W is the full data set. The conditional mean of YI given XI has some functional form like this. Okay, which is nonlinear. Why? Well, again, you see, the linear structure is a very special structure that typically does not come out of economic theory at all. Right? So in many cases, you might want to go to the underlying nonlinear model. For example, if you are estimating even a simple production function, right? Take let us say, a Cobb-Douglas form. What is a Cobb-Douglas form? Cobb-Douglas form is, let us say, y is equal to A capital to alpha, labor to beta, right? Now, what can you do? Typically, what we have done so far is we have converted this into logs to make it log, because this is in log linear form, right? So what we have done is log y is equal to log A plus alpha log k plus beta log L, and we add a epsilon. So here we make it log of this epsilon. Okay? Now we can do standard ordinary least squares and anything else here, right? But remember that our theory was specified in terms of y, whereas our estimation is in terms of log y. Suppose we have an excellent model here, that does not necessarily give us an excellent model to understand output. Okay? Suppose we wanted to estimate this directly. Our function here will be a nonlinear function then. So those are the kinds of contexts where we want to use nonlinear least squares. Okay? Is it difficult? No, it's not difficult. What we do is that this guy is at the true parameter value. We define our errors as the difference between these two. Remember, this is not this epsilon here, right? So we have a plus then, yeah? I'll say plus epsilon here, and I will say log eta here, okay? So just to make sure that these two errors are different in character. And we make this assumption, the exogeneity, typical exogeneity assumption, and we have an M estimator which minimizes the sum of squared residuals. What is that? That is minus epsilon I square is our M, and then we sum it across all individuals, right? Okay. So our Qn is this guy here. But the rest is very simple, right? Okay, so now there will be nonlinear optimization to get at this. Okay, we're not simplifying this further, right? Because it depends on the complexity of this P function. Okay. Simple. Okay. Nonlinear GMM. We'll go into maximum likelihood, but after a very short break. All right. But any questions so far? Any questions about GMM as well? That sort of completes our discussion on GMM. We'll be coming back to it in various ways. We'll be coming back to it in panel data, where we'll be doing some GMM. We'll be coming back to it when we do discussion on identification, right? But the mechanics of GMM, we have already covered that, right? And the the mechanics is already done. Okay? Right? 5 minutes. Okay. Did anyone check whether the recording went okay last week? Can you please check perhaps at some point and let me know? Okay, we'll make a start. I want to mention one other thing at the beginning right now. The lecture notes and the way we are covering it has undergone major transformation this year. Hopefully it is for the better for you guys, and that is why there is TB here. TB was one of the students in the SGPE course last year, so I took his help to try and organize this in a pretty major way. Now, we need some help from you guys as well, so if we can have some feedback as to how the lecture notes are going, which parts you perhaps found it more difficult, more intense. That helps in two ways. One is it helps redoing the course again next year, but it also helps our discussion on the fifth day, right? So today is the third day, but on the fifth day we are going to have a discussion, and maybe we'll come back to certain parts of the course and do that again, right? So if I can have some feedback about it, that will be brilliant. I have tried sending you an email yesterday. I don't know whether you guys have received that email. You can respond to that. It will be actually more helpful for me if you can also copy in my Harriet Watt email address, and I'll put it down here. AB, it's my initials, 580 at hw.ac.uk. The only reason for doing this is that I check my Edinburgh email probably once a week, right? But I am continuously checking this one, right? So, kind of, I'll get to that quicker if you were to correspond with me. Okay. In particular, maximum likelihood has undergone major changes. So I'm particularly interested in what you think of this. So let's go on with it. Typology, I'm not going to cover this because we have already done it, right? So if it is done on separate days, different days, then I would cover that again, right, just to get your thoughts on it. We'll really start from here, the formal apparatus of maximum likelihood, likelihood scores Hessians. Then I'm going to take two simple examples. One really, really baby example, right? That is going to be this binary response example. And another one, because you guys have seen this in several ways already, right? So we're going to take that example to set our concepts in place. Then we will talk about the asymptotic properties and testing, leading up to probably the most important thing here is this Cramer-Rao inequality, and together with another important concept as well, which I'm going to come to in a few minutes. And then we are going to do several examples. These are not numerical examples, right? But we are going to take several models and try and look at maximum likelihood in this context. When we do maximum likelihood in this context, of course, straight away you can see from the first one, you cannot straight away see, but you will see very soon when we discuss that, we are also going to put ordinary least squares on the board, right, as an alternate estimator. And we are going to also discuss a little bit of GMM in that context. Then classical regression model again is revisited. Now this has been revisited several times. Now we are going to do it. When we do it now, we are going to put least squares on the board, we are going to put GMM on the board and maximum likelihood on the board, all three. All right, and we are going to have a discussion of that. And there will be several other examples, and not all of these I'm going to cover in lectures, because one of the feedbacks from previous batches is that it becomes very heavy. They are there on the slides. So have a look at those, and in line with past exam questions. So then you will get a sense of the kinds of maximum likelihood questions which might come up, right? Obviously, the other examples here are a bit more complex. All right, I'll be briefly introducing those, but going off. If you have trouble going through the slides, then we'll come back to it later on. Okay, so that is the idea. Okay, Hayashi chapter 7, and then 7 and 8. Okay, so that will be our standard examples, though maximum likelihood is actually covered very well in the other books as well, right? So Verbeek is very good, and Green is also very good. By the way, are you guys reading books? Reading books is very important, guys, because you see, there are different, when we do lectures, we try to do it in a way that is relatively inert to different ideological or disciplinary perspectives, right? So that is the way we do lectures, right? So if any of my own philosophical or disciplinary perspectives or preferences come into my lectures, that is not intended, right? We try to do it in a very inert way. But when you look at books, you get the different perspectives. So different people approach it in different ways, and probably the hardest of all the books here is this one here, but it is also the most fruitful. Have a look at Green. You know, kind of Green is very concise, very, but extremely scholarly, and you know, kind of it's like, you know, a very concise Bible, if you may, you know, kind of. So that is the way the book is written, but it is enormously fruitful, actually, to look at Green's treatment. Okay, that's an aside. Concepts, maximum likelihood estimators, likelihood and log likelihood functions, and then various other things. Okay. Likelihood ratio test is also part of concepts, and then other things. Key terms: likelihood, log likelihood, conditional density, likelihood contribution of an observation I, then score, Hessian information matrix, then the estimator, then various kinds of tests. We are coming back to the tests now again, right? So this is the second time we are coming back to different kinds of testing principles, right? So we'll see the contrast now, and various models. Marginal effects are important because typically, historically, this is a slightly easy thing for us to examine people on, right? And there's also a lab relating to this. Okay, so that's why. Okay. Terminology, once again, okay, so this is repetition. So I will not do this. Okay. What was the central intuition or the central idea behind least squares? Well, the central idea behind least squares is you have observations yi. They come from some model of the data and involving some parameters, right? You take the difference of these two. That is what? That is your epsilon I. You do not care whether these differences are positive or negative. So you take a square. You sum these over 1 to n observations. And you want to minimize this. With respect to theta, equal to minus. Sorry, what am I doing? I put the equal in the wrong place, but that's okay. So theta hat is equal to this. What is the principle here? So I'm saying least squares, so this also includes nonlinear least squares, right? So ordinary least squares and nonlinear least squares. So basically you're saying, well, my data is y. This is my model. If my model is good, then my errors should be small. How do I know my errors is small? Okay, I can take the squares of those and sum over all the observations, and that gives us a metric. I want to minimize that metric. Okay? When we did GMM, we obtained a distance. A distance between what? Distance between what were the theoretical moments, moment conditions, right? And the moment conditions that come from the data. And because the theoretical moment conditions are in general more, so we have to use a weighting matrix here. So what were we trying to match? We were not trying to match y to its prediction. We were trying to match the theoretical moments to the empirical data moments. Okay? So that is what we were doing in GMM. Here we are going to talk about quite a different estimation principle or principle of inference. Okay, and that is quite dramatically different. So what are we saying? So we have some data, yi, xi, At the moment, we are very general about what our true model is. These data, they are generated by some assumed data generating process. And we know that data generating process, or we have assumed that data generating process. Except that there are some parameters in that data generating process, some parameters in the population that we are not sure about. But except for those parameters, we know this data generating process completely. So we take as given, or we pretend we know, the functional form of the DGP, including all distributions. So we know things fully here. The functional form of the DGP depends on some parameters which we don't know. These parameters have a true value which is theta naught. Theta is some arbitrary value or an estimator, and theta hat ml is the maximum likelihood estimator. Now, as opposed to the previous two cases, we have an advantage here. Or, in other words, we have made stronger assumptions. And what is that assumption we have made? We have assumed that we know the full data generating process fully, except for some parameters, parameter values. Because we know this fully, then that provides us an alternate way to look at inference. And what is that way? So suppose we choose some values for our theta. We know the DGP fully, so we can write down the probability of the data. Okay? I'll come at it slowly, right? So, we have a data generating process which is specified fully, except that there are some parameters that we do not know. Only some parameters, right? It's finite dimensional. We can plug in some values. If we plug in those values, we can write down the probability of the data exactly, right? Now, because we can do that, now we can do a different kind of thought experiment. So let us say we have one choice of parameter vector, let us say theta 1, and we have another choice of parameter vector, let us say theta 2, and now we can write down the probability of the data if theta 1 were our true parameters and theta 2 were our true parameters, and ask which one is larger. That's a natural thing to ask. Why can we ask this question? We can ask this question because we know the data generating process fully. So then that is a natural question to ask. So then we can say that if theta 1 gives us a probability of the data which is larger, then maybe theta 1 is more likely to be the true parameter values. Okay? So we have turned the question the other way around here, right? In a sense that I'm going to formalize in a few minutes. But what we are doing here is that we are saying, okay, we don't know this theta guy, right? Okay, so that's the problem, right? So what do? Let us assume some values. And if we have two sets of values, then we can run a horse race to ask which one explains the data better, in what sense, which one gives us a higher probability for the data that we have observed. Okay? And that is the principle that is called the likelihood principle. So what is the method of likelihood? You choose as the estimator of the true theta naught that guy which maximizes the probability that our sample data was generated by the assumed DGP. Okay, straight away you can see that the principle here is very different from those two principles there, right? Okay, so it provides a different principle of estimation or inference. Okay. There is a catch here, and that is, so far I have been using the words probability and likelihood somewhat interchangeably, right? Now I'm going to become more technical and try and understand why those two are different and how those two are different. Okay, and that will bring us to the question of the likelihood principle. In order to do this, let us start with a small example. Yeah. Mickey Mouse example, very simple. Okay. What we do? We have a limited dependent variable. What is a limited dependent variable? A limited dependent variable is a dependent variable, but its value is limited. In this case, it is just a binary response variable. Yi takes the value 1 or 0, or yes or no. Examples, labor market state, 1 equal to employed, 0 equal to unemployed. Consumer choice, buy a car, don't buy a car. Come to lectures, don't come to lectures. Right? Okay, so that kind of stuff, right? Okay, so why is a discrete action? Enter the labor market, stay at home. Okay? So maximum likelihood is a way forward here. So let us look at this specific example, very simple example in some detail, right? You have a very simple model here. For the moment, there are no regressors at all. Yi takes the value 1 with probability theta naught. This theta naught is unknown to us. And yi equal to 0 with probability 1 minus theta naught. Let us say our yi is employed and unemployed. Then what is the theta? Theta naught. So 1 minus theta naught is the unemployment rate, right? Theta naught is the employment rate. Okay, keep that analogy in mind all through. Okay, so very simple case. We are not regressing. There are no x's here. Very simple situation. We want to do this. Okay, so what is our DGP? DGP is completely known here. Yi equal to 1 with probability theta naught. Yi equal to 0 with probability 1 minus theta naught. This is a simple Bernoulli. You guys know everything about the Bernoulli, right? So we can very easily proceed. What is our data? We are going to n individuals in the population, randomly selected, IID, simple random sampling, and we have collected their labor market status, Yi. So this Y1 through Yn is just a collection of ones and zeros. Okay? So how will we find out what our true theta naught is? Well, we try to do maximum likelihood, so we want to maximize the probability that this sample of data is generated by this data generating process. Okay? So, in order to do that, we have to write down probabilities, right? So for a single observation, what is the probability that yi equal to 1? That is simply theta naught. We have n observations. Because they are IID, we can order them in any way. So we have ordered them so that n1, which are the ones in our data set, they come first and then the zeros. This makes life a bit simpler. Okay? Suppose our sample size was 6. And we had 2 which were ones and 4 which were zeros. What is our best guess of theta naught? 2 by 6. Right? Makes sense, right? So we know nothing else, right? So in this small data set, in this small world, that has to be, kind of a place to start. Okay? Unambiguous. Suppose we were guessing that theta hat equal to 0.1, that is pretty silly, because that is not 1/3, right? It is much smaller than 1/3. Okay? Suppose we guess this value, what do we expect? We expect that compared to 1/3, the probability that we get of this particular data will be smaller. Okay, let us find out whether that is the case. So y equal to 1 with probability theta naught, y equal to 0 with probability 1 minus theta naught, n1 equal to 2, n2 equal to 4. Now we denote by L theta. L stands for likelihood, right? What is that? That is the probability of observing this number of ones and zeros for a given theta. Okay. So let me do a little bit of conceptual thing on this side. Typically, when we do a probability calculation, what would we ask? We would ask the probability, so what is the probability, let us denote this probability by F, of n1 equal to 2, n2 equal to 4, given, how do you write given? Well, typically in slides I write it as a semicolon, but on the board it doesn't work out very well, so I'm going to do this, okay? It's fine, right? Suppose we knew theta, then this would be very easy to write. Right? Very simple. We can write down that probability. Everybody here can write down that probability. I'm going to call this f of the data x or w or whatever given theta. What is this guy a function of? That is a function of the data. Hang on a minute, that's not the problem that I was wanting to address here in the first place, right? Because the problem here, I do not know the theta. I'm given the data, right? So I'm not in the business of writing down a probability of the data. My business is writing this in the other way around, right? Same function, but think of this as a likelihood of a theta given the data. I can always do that, right? The same function, I can interpret that as a probability. When I interpret that as a probability, my arguments are the data. And what do I know? I know the theta. But in this current business, of course, the data is given to me, right? I have my sample data. I will interpret the same guy as a function of the unknown theta. If I do that, then I have some options here, right? I can ask the question, what value of theta best represents my data in the sense that the probability is highest? Okay, so that is the kind of question that we are going to ask. Okay, so L theta is the likelihood, okay? It is a function of theta, not of the data, right? The probability of observing this number of ones and zeros given some theta. Okay? And now we are going to write down this likelihood now, not for individual observations, but for the whole data. Okay? How do I do that? Well, I've done simple random sampling. My setting is IID, very nice and simple. So I can just simply take the likelihoods of each individual observation and multiply one with the other. Okay, the start thing there is a multiplication, okay? Right? That's it. That's my likelihood of the data. So suppose my order was like this. I can take any order, right? Because this is all IID, right? Which order it arrives does not really matter, right? I'm not doing time series here, right? Okay, so I can set it up in any way. So I put the these two guys at the top. What is the probability of obtaining a 1? That is a theta. Another one, that is another theta. And then 1 minus theta times 1 minus theta 4 times. So this gives us this. So the likelihood of my data then is simply theta square 1 minus theta power 4. This is a convex function, so I can maximize this. Okay? Right. Terminology issue. Distinguish between the true parameter theta naught. The true theta naught appears in the data generating process, right? Any possible theta is some value of this true parameter. Okay? This possible theta appears in the likelihood function for observation I. Okay, so that we denote that by Li theta. Okay, and because we are in an independent world, sorry, I'll shut down the volume here. Okay. So because I am in an IID world, this is just a product. Okay, product of Li theta over all the n observations. Suppose I could maximize this, then that would give me the maximum likelihood estimator theta hat ML. Okay. So I've covered this already, but just to go over this again, conceptually there is a difference between what is the probability and what is the likelihood. What is the difference? The functional forms are the same. When we are talking about the probability, it is the probability of the data given some parameter value theta. When we are talking of the likelihood, it is the likelihood of the unknown parameter theta given the data. Right? Functional form is the same, but the difference is whether you look at it as a function of the data or you look at it as a function of the parameter. Okay? So the PDF for observation I is this guy, right? That is in our regression setting, for example, right? And the likelihood is simply this guy. Okay? But this is looked upon as a function of the theta. Okay? Back to this example. Our likelihood is this guy. Maximizing is very easy. We are going to find out soon that one easy way of maximizing is actually taking logs. Why? Because the likelihood function is a product, right? If you take logs, it becomes a summation. If it becomes a summation, it becomes like a moment. Okay? We find it easier to handle moments, so we take logs. Okay? Right. So log L theta, and log is a monotonic transformation, right? So whether you maximize L theta or you maximize log theta, log L theta is the same. Okay? All right. So this guy. Okay? And now you guys can solve this easily, right? Yeah, so very simple, first order conditions. Oh, hang on a minute. Theta hat ML is exactly 1/3. Okay? Right? You got the idea, right? Okay? If you have got this, you have got the concepts in place. Okay? The rest is algebra. All right? We'll go through that. Okay? Right. So, in principle, the first order conditions are not enough. Why? Because you want to maximize, you want to maximize the likelihood, right? You want to make sure that you are maximizing and not minimizing. So you have to look at this, the second order conditions as well, right? Okay, so second order conditions, we'll be coming back to that. That is very important. Okay. In this case, I'm saying check it out, right? You guys write it down and check. Okay? So that's very easy. All right. More generally, we have n observations. N1 is the number of ones, N0 is the number of zeros. So our likelihood function is like this, log likelihood is like this, first order conditions, theta hat ml is N1 divided by N0 plus N1. Okay, so this more generally, this will happen. That was a very simple example. So summarize, we specified a DGP with an unknown parameter. We found expressions for the probabilities, right? And then we interpreted the probability as a likelihood, right? As a function of the unknown parameter, okay? And then maximized it. We chose theta, that maximizes this guy. That is the maximum likelihood, okay? What is the likelihood principle here? Likelihood principle is simply saying that if you have two different candidate parameter values, if one of them gives a higher probability of the data, that must be more likely. Okay, very simple principle, right? So, but that is called the likelihood principle. Now, this is used in a variety of different ways. You are going to see lots of uses of this in this course, in Econometrics 2. But some of you guys might be doing Bayesian econometrics as well. There it is entirely based on the likelihood principle. Right? So the likelihood principle is actually a very important principle. Okay? Okay. With maximum likelihood, we need to specify the full DGP completely. What does that mean? This was a very simple example. In the linear regression case, we have to specify the functional form. We have to also specify the distribution of the errors. Now, if you had endogeneity, if you have to specify the distribution of errors conditional on each value of x as well. You need a model for it, right? A fully specified model for it. That is a lot of assumptions. Okay? If the maximum likelihood distributional assumptions are correct, then maximum likelihood will not only be consistent but also efficient. I'll be coming back to this a bit later. Okay? However, if the maximum likelihood distributional assumptions are wrong, then the maximum likelihood estimator can be inconsistent, and that is bad news. Okay? In this case, something like GMM that makes fewer assumptions may be better. I'll be coming back to discussion of it. It turns out that in some cases, the maximum likelihood might still be consistent even when the distributional assumptions are wrong. That is called quasi-maximum likelihood. I covered this only in passing this year, all right? But it is a start of a different side of the literature, right? So if you guys are interested, I'm happy to discuss that further, okay? Quasi-maximum likelihood I cover only in passing. Okay. So now the general case. Conditional density for observation I is the probability of yi given xi and theta. I've written this in this particular way to emphasize the fact that xi is fixed by design potentially, right? Okay, but it may not be, right? You may have yi xi together there, right? And just this theta here. And the likelihood contribution has the same expression, but is interpreted now as a function of this theta. Okay? So likelihood contribution, we are going to simplify the notation and just call it Li theta. Suppose we are in an IID world. Well, why IID? Just independence will be fine. Suppose we were in an independent world, then the likelihood of the data, okay, is simply the product of the likelihood contributions of each individual data point, right? So they are independent. So this is the likelihood of the sample of data. The log likelihood is simply a summation, which is nice because we know better how to work with summations, right, or means. So what is the maximum likelihood objective function? That is this guy. Why? Because we are maximizing this, right, which is the same as maximizing this. I just added a 1 by n here, which is a scaling factor, to emphasize that this is actually like a sample mean. All right? So then the entire mechanism of means, moments, carries through. Okay? And this is an example of the extremum estimators that we have looked at earlier, the M estimator in particular. Okay? This is my objective function then. How do I maximize this? Well, let us assume that this thing is nice. It's convex everywhere, you know, so all the nice properties. Then what can I do? I can take the first order conditions and just set them to 0 together. Okay, so that is how you maximize a function, a nice function. All right, so SI theta is simply the partial derivative of the log likelihood of an individual data point with respect to theta. This is a vector, right, across all the theta elements. And the score vector for the sample is simply this guy. Okay, we are going to equate this to 0. Right, there are some notation issues. You guys take care of that. And so the score for the sample is the gradient of the objective function. Well, we have taken the gradient, equated that to 0. What makes us so certain that we have got a maximum? Well, we are not certain at all. We need to check the second order derivatives, right? So the second order derivatives are called Hessians. Okay? So if my theta was p-dimensional, my score vector is p-dimensional, right? That's one element for every element of theta. What is this guy? This guy is a p by p matrix. Okay? So the Hessian for the sample is simply second order derivative of Qn with respect to theta, del theta, the del theta prime. All right, and that is also can be written as a sample average. So now this is my Qn, very simple. This is my score vector for each individual observation. I've aggregated that for the whole data, Sn bar theta. This is my Hessian for every individual observation. Yes, please.
I got lost in the notation. What's P again? Where does that quantity come
I have not been explicit about it, but theta is p dimensional. Okay, so let me. Theta is p by 1, so my SI theta and SN bar theta, these are also p by 1. And my HI theta and HN bar theta, these are p by p. Okay, these are metrics of second derivatives. Okay. Typically these matrices will be symmetric, right? Usually, not always, but usually. In the cases that you will find, they will be symmetric. Okay. Why? Because whether you take the first partial derivative with respect to the first one first or the second one first does not really matter, right? Okay. So okay. So then our theta hat ML is simply argmax of this guy. Okay, the important thing, conceptual thing, is the distinction between these two guys. And I think I've discussed that several times, but should be clear to you guys, right? So it is the same function, see, but it is a question of how you look at it. Whether you think of that as a function of the data given the parameter value, or you look at it as a function of the parameter value given the data, right? So it's a question of looking at it. All right. So I'm repeating myself here. What is important here? Observation yi xi is IID. I've assumed that for the moment, certainly. This will be broken down later on, right? In Econometrics 2, we will come to situations straight away where this will break down. Okay? But for the moment, let us proceed with this assumption. And the independence here is needed for this formulation. Why? Because without independence, the joint probability is not a product of the individual probabilities, right? So the independence is absolutely key here. Okay. Right. First order conditions. This is the score vector for an individual observations. This is the score vector for the sample. So what is the maximum likelihood estimator really? It is setting the score for the data to 0. When you set the score for the data to 0, how many equations do you have? The score has how many elements? P elements. So there are P equations. In how many unknowns? In P unknowns. Alright? Hopefully you can get a solution, right? If none of those conditions are redundant, you get a solution. Okay? And well, whether it is unique or not, well, I'll come to that. Okay. Now, what are the properties? The maximum likelihood estimator is consistent for theta naught, provided, of course, the model is correctly specified, right? The DGP is correct, and there are some other conditions that I'm going to come to a bit later, right? I'll discuss that slightly non-technically, but we'll still discuss it. It is consistent, it is asymptotically normal. The maximum likelihood estimator is asymptotically efficient. Actually, in many cases, it is going to be efficient even in finite samples. And the asymptotic variance of the maximum likelihood estimator is this guy. Okay? Now, let me straight away point out why this is so important. What is my HI theta naught? This is my HI theta, right? What do I need to do to this to get to HI theta naught? I need to know the true value. But that is the problem, right? I don't know what the true value is. However, I'm doing maximum likelihood here, so I have a consistent estimator. So I can substitute that here. Okay? But this is not what I want, right? What do I want? I want the expected value of this. So how do I get the expected value? Oh, hang on a minute, I have n observations here and this is the expected value. This is my best guess for the expected value. So in the process of calculation, you have already calculated your Hessian, right? And that straight away is going to provide you an asymptotic covariance matrix, right? So all you have to do is invert that matrix. Okay? So the observed Hessian, so this guy at theta hat ml, that converges in probability to this guy. Okay, so that is now straightforward, and therefore you have a consistent estimator of the asymptotic variance of the ML estimator. Okay? Nah, too much. Okay guys, so far so good? See, in terms of how it goes in this course, I think this is, I personally think this is lighter, right? Okay, so we will get there, so we'll do quite a bit. I think we are making good progress, so we'll get there. Okay, any questions so far? Okay, we are leaving most of the exciting stuff for the afternoon, right? So we have just done the Mickey Mouse binary example now, right? In the afternoon we are going to do regression, right? So then it will be good fun. Yeah? All right, so we meet in 1 hour, okay?